Alex is a current graduate student at the University of Tennessee and will be receiving his Masters of Science in Nuclear Engineering this coming December. Alex previously graduated with a BS in Nuclear Engineering from North Carolina State University and has given talks at the past 3 consecutive INMM national meetings in the area of safeguards and non-proliferation. This past meeting, he presented some of his thesis research on alternative helium-3 technologies for use in radiation portal monitors, work which he has continued to develop and will be expanding upon today. I will also take credit for Alex as one of our Okowita interns as well. So thanks, Alex.
Keep that thing really quick. Well, thank you for that introduction, Luis. As you said, I'm going to talk about some of my work that I've done in my thesis that I just finished up yesterday. Just finished up with my thesis. I first wanted to talk about some of the requirements for neutron detection in general. So what you really want is a high efficiency detector, so the ability to detect as many neutrons as possible. You want to have a high effective discrimination against gamma rays, so not miscounting gamma rays as neutron events, and also the ability to maintain their neutron detection efficiency in the presence of gamma rays. So when you have a gamma source and a neutron source, you don't either overload the detector with counts or you don't miscount a significant amount of gammas as neutrons when they're both present. So I'm sure some of you know about the problems that we have with helium-3. Helium-3 is kind of the gold standard of neutron detection that we have now. After the events of September 11th, the demand for this material significantly increased for the already diminishing supply of it. So this has caused a kind of inexorbitant amount of money being needed for these detectors for their safeguard use, specifically in radiation portal monitors at border crossings. So this is kind of the non-technical requirements for this neutron detection with these alternatives. Since you already have these radiation portal monitors in existence, these alternatives need to be able to kind of plug and play with the existing systems. They need to be able to be placed right in where the old helium-3 was. And this list kind of overviews some of the considerations you should have when thinking about alternatives. They really need to kind of hit all of these points. So our goals, or my goal in this project, was to take a current alternative that's already being deployed in the field, so an existing portal monitor, and analyze it for neutron efficiency, gamma ray response, temperature dependence, and moderation response. I did all my work at Oak Ridge National Lab in some of the different facilities that they have. So for an example, this is our helium-3 module that we used. It's a TSA or Raviscan typical helium-3 module that's put into radiation portal monitors. It's two 2-inch diameter tubes with an atmospheric content of helium-3 of 2 atmospheres. On the left there you can see it. That's with the faceplate, and then without the faceplate where you can see the 2 helium-3 tubes. I also tested this against an Aspect lithium zinc sulfide detector. So it's a lithium-6 coated zinc sulfide scintillator that's doped with silver in order to increase light movement into the photomultiplier tube. So since this is a scintillator, it does need a photomultiplier tube in order to detect the counts. On the left is a picture of the inside of one of Aspect, which is the company that we bought this from. It's a company in Russia. That's one of their cabinets that they have for their radiation portal monitors. On the left of right here is their gamma detector, which is polyvinyl telluride, or PVT. And on the right is their lithium zinc sulfide detector. And the right picture there is the actual module that we used for our testing. So this is kind of our experimental setup. That cart on the right there is one that I built out of 80-20 aluminum, and if you've never worked with it before, It's kind of like working with Tinker Toys. So I got to go back to my engineering roots, I guess, when I put this together. But each detector was placed 1 meter apart, and the center points were 1 meter off the ground. So those yellow dots on each detector are the center points, and those were located 1 meter off the ground to prevent against scatter from the floor for our experiments. Our first experiment using this testing setup was a neutron profile. So the source, we placed the californium source 1 meter away from the detector faces and ran it 3 meters to the left and to the right laterally along it to kind of emulate a car driving past the detector, and took our response data. So you can see from this plot, that's our mean counts per second at each half-meter point along that interval, and it kind of makes this profile curve. So as you can see, lithium-6, although it is lower than the helium-3, it's not a whole lot lower. So it's definitely in consideration for this alternative. It can do the same things. I also did a moderation response. So these spheres are nested polyethylene spheres, with the smallest one you can see on the right. It has a thickness of 1 centimeter, and then each successive sphere that you add onto that adds another 1.5 centimeters of moderation, up to a maximum of 8.5 centimeters. So you can kind of get a moderation curve, a moderation response of the two detectors as you increase the amount of polyethylene on them. So for the most part, standards kind of have them, you calibrate each detector to a bare source. So the lithium-6 curve that you see on the bottom there is kind of what you would expect if that were the case. Where as you increase your shielding, your counts per second, your count rate would go down. What we found interesting was the TSA modules, they purposefully under-moderate their detectors, so you can see as the curve goes up before it comes back down. This was done under the assumption that some sort of nefarious actor would have the foresight to shield their material before they tried to go through one of these monitors, so they would actually be increasing the response of the detector instead of decreasing it by shielding it. We also did environmental testing in one of the environmental test chambers located at the lab. We placed both of our modules on aluminum table, and the source stand there is holding 2 californium sources about 1 meter high off the ground, off the center point of the face of the detectors. And they were placed in this environmental testing chamber, and we changed the temperature from negative 30 degrees Celsius to 60 degrees Celsius, and we took measurements at every 10-degree interval, and we allowed the detectors to soak for 2 hours at each temperature so that they would become, I guess, nominal to the environment. So here you see the temperature response of these detectors. The ideal response is kind of a flat line, which you can see with the helium-3 detector. Within some sort of statistical accuracy, you can see that it's pretty much a straight line all the way across our bounds of negative 30 to 60 degrees C. With the lithium-6 detector, it actually decreases as soon as you hit around 20 degrees Celsius, so room temperature, it starts to decrease. This is due to thermal noise in the photomultiplier tube. So it's not a problem with the lithium-6 itself, but more of a problem with the photomultiplier tube attached to it. Here's some other important metrics that we tested for, the absolute neutron detection efficiency and the gamma absolute rejection ratio for neutrons. So the absolute neutron detection efficiency is the number of counts counted, or the number of neutrons counted by the detector over the amount of neutrons released by the source. And it has, the requirement is in some documents of, this is the requirement they need to hit to be considered as an alternative. As you can see on the left side of the plot, both of these detectors, both the lithium-6 and the helium-3, both fell above this kind of threshold that we were testing against, and they have a very similar response. The gamma absolute rejection ratio for neutrons is basically how the detector responds to having a gamma source and a neutron source, like I mentioned before. So how we tested that one is we placed a cesium source 20 centimeters from the detector and a californium source 1 meter away from the detector and took a measurement. And it's supposed to fall within those bounds of 10% change from just a neutron source in either direction. So you're trying to get more, or trying to stay in the middle. It's basically trying, you want to have an ideal response of 1. So your counts with a neutron source and with a gamma source present should be the same. So as you can see in this plot, they are pretty much equal. They're 1. They both have a similar response to the gamma rays. It didn't really affect either detector. I didn't actually mention how we tested the neutron detection efficiency. We placed the source 2 meters away from the detectors that we had, and that's the response that we got. So after we tested all these metrics for the lithium-6 detector as well against the helium-3 detector, we found that lithium-6 is a really viable alternative to helium-3. It has a high absolute detection efficiency, a high neutron detection efficiency when exposed to gamma rays, and it also has the ability to maintain its detection rate at all operational temperature ranges, which we tested the negative 30 degrees Celsius to the 60 degrees Celsius. So, I'll be happy to answer any questions you may have.
Alex, I wasn't privy to your presentation this summer, so can you tell us where you were at what point at that presentation, and then what you added on to complete your thesis?
So at that presentation this summer, I had only done the profile curves for each detector. So I'd only gotten that kind of bell curve profile response. And this summer, I really tested pretty much everything else in the thesis.
A lot in short.
For sure. Right.
Do you have any idea of the cost, sort of like a cost-benefit analysis leading to 6 versus 7?
So I never actually went into kind of how much this lithium-6 detector would cost. I know it falls within kind of the range that is needed. It falls under $30,000 per system, but I don't know the cost that goes into each specific part. I know it's really hard to basically separate the lithium-6 from the lithium-7. So I don't know exactly what the specific costs of that are. Yes?
Did you find any disadvantages? So if somebody was asking you, what's my pros and cons of going ahead and replacing lithium-6 now, what would your response be on the pros and cons? Did you have any?
So the question was pros and cons of lithium-6. I'd say the pros are, it has a similar response to helium-3 between the neutron detection efficiency. I would say the cons probably the temperature. You notice the curve, it goes down by almost 20% over the full interval. So if you live in, or if you're putting these systems into a really hot environment, you may consider using something else. That would probably be the biggest con that we found of it. It does have a lower response than helium-3, but they are very similar as an alternative. Blake?
What was the enrichment of your lithium-6?
Lithium-6 is 95%. It's 90. I think it's between 90 and 95% lithium-6 to lithium-7.
Do you anticipate any difference in your operating characteristics based on that enrichment?
So I know you want a really high efficiency of lithium-6 because that is the detection medium, and any lower than that you start definitely trailing off. So that is kind of the standard to have that between 90 and 95% enrichment. Any other questions? Chris?
How often do the detectors encounter those temperatures where you lose 20%?
So so the operating temperature range of these detectors is supposed to be between negative 40 and 50 degrees Celsius. We didn't want to go too cold because we didn't want to break the detector, to be honest. We went a little bit higher than that range because the 60 degrees Celsius, you don't really expect that much. But when you live in a really hot climate, these detectors are put in basically this metal box. And if the sun's beating down on them, they're going to get really, really hot. So you really only expect those kind of massive temperatures at 60 degrees Celsius in a very hot environment on a very hot day. Anybody else?
I guess I was just wondering one more thing.
Sure.
How those detectors scale? What's the largest physical size you could get with maybe a lithium-6? Do you have a feel for any kind of size limitations?
I don't know specifically about size limitations. I assume it's along the same lines as your PVT, since it is a scintillator, so you're really limited by the amount of light yield you get out of it. But these detectors, the one I tested, can fit right into an old TSA box, so it can fit right where that volume of helium-3 already was.
Okay, thanks very much, Alex.
Thank you.